Welcome. Thank you all for coming out this evening. My name's Sarah. I'm the lead camp and adult programs coordinator here at Vince, and I am very excited to introduce Mackenzie Jones for you tonight. She's going to be sharing some of her kind of things that she's the most passionate about. That's the great thing about Brain Buzz is we get people here who are excited to talk about their work, but also talk about things in their field that may not necessarily align right with their research, but are kind of their passions. So tonight is no different. And before we start, a huge thank you to the Upper Valley Food Co-op and the Dartmouth, I'm going to get it wrong, School of Graduate Studies. I did it. They changed their name last year, and I still can't get it right.
We're an official school.
You are not
yes.
alone on that, let me tell you. Even people on campus.
Yes, yeah. So they're our co-sponsors for this event, and we're delighted to partner with them to bring current science and research to our community. So thank you for coming out. And we've got CITV here tonight, who's going to be broadcasting. And there are plenty of refreshments, so please feel free to help yourself. Coffee will tempt us all night. Keep your fingers crossed, because there was a little break in the clouds, and we might be able to see something.
Don't cross your fingers the whole time. Should be paying attention to me instead. So, like she said, my name is Mackenzie Jones. I'm a graduate student at Dartmouth College. I'm currently a PhD candidate, which means I'm fancy and almost done. I'm in my 5th year, so don't ask me what I'm doing after this, because it is a very sore subject. So my research area is in supermassive black holes in the centers of galaxies, and that sounds really obscure and far away because it is really obscure and far away, but these supermassive black holes are actively eating gas and stars, and basically they emit as much energy in 1 second that could power the Earth's energy consumption for longer than the universe has been around in 1 second. So they're really cool objects. I'm not going to talk to you at all about them, but I should reference it because I am wearing my Hidden Monsters, or an active supermassive black hole that's currently obscured by gas t-shirt. So, what I am going to talk about is Edward Pickering and his women computers of Harvard. And the reason I'm going to talk to you about this is because I'm a woman in astronomy, and that is still a very rare thing to be. And a lot of these women that I'll be talking about tonight were the very first of their kind, doing a lot of this really great research. And a lot of what we still use today, they established and is currently being attributed to men. So, it's going to be exciting. I have to start this talk talking about Edward Pickering, William Pickering is his brother, who made some other really great advancements. Edward Pickering, who was the director of Harvard Observatory from 1877 to 1919. And I'm going to be throwing lots of facts at you, and I'm going to be throwing some astronomy at you, so please interrupt me if you are confused or just are tired of me, like, reading off my paper. We can have a conversation, it's okay. Okay, so Pickering was the leader in Harvard's work of photometry, which is measuring the brightness of stars, as well as spectroscopy, which is looking at the composition of stars. And to do that, you take a light at the stars and you can break it with a prism, and you kind of see all the different lines. Okay, that doesn't mean anything to you, but what you get... Well, you're an astronomer, so what you get is the rainbow broken out, and there's some black lines in it, and those black lines represent different types of elements. We're all on the same page. Spectra are great. They tell us a lot about the stars, but back then they didn't know what spectra were or what those lines were or anything about the composition of these stars. But anyway, another thing I'm going to mention a couple times, which I should get out of the way and just define for you, is something called a magnitude, or how bright the star actually is. So you can look at a bunch of stars and be like, oh, that one's much brighter than that one is, just with your naked eye. You can call that a magnitude. And you can make any scale up that you want in the entire world, because it doesn't matter, there's not one scale. So the magnitudes that I'm going to be talking about, the scale, is where a magnitude of 1 is 100 times brighter than a magnitude of 6. Our naked eye can see a magnitude of 6.5, and no lower. So a magnitude of 9 or 10, you need a telescope to see a star that dim, or a galaxy that dim, or whatever. So Pickering is doing all this really great work, getting money for all these telescopes on Harvard's campus, and he has thousands and thousands of observations. He can't look at all of those observations at one time, especially because it's not computerized like it is today. You can't take a digital camera, take a picture, and have it run through a machine. You actually have to have someone look at every single one of those images. The images I'm talking about are photographic plates. Photographic plate looks like this, because this is a picture of a photographic plate. It is a glass plate that is very delicate, and you can't smudge, and it has all sorts of fancy things associated with it. Basically, it's a glass plate of stars, and it's clear. The stars turn out black or whatever nebula is there. Cool. So he has thousands of these, and he needs someone to look at them. Well, you need someone to do the math. You need someone to look at them. Who do you pick? Women. Women, according to Pickering, have great attention to detail. They can tolerate repetition, and also you don't have to pay them very much. So I'm going to read you a direct quote from Pickering, which is, talking about the wage gap early on. Women are capable of doing as much good routine work as astronomers who would receive much larger salaries. 3 or 4 times as many assistants can thus be employed and the work done correspondingly increased for a given expenditure. So, Pickering could hire 4 women to hiring 1 man, which is what he did. And their salary, their hourly rate was 25 cents per hour, which, if you account for inflation, is less than $6 an hour today.
Excuse me, what time span are you talking about?
So this is, 1877 to 1919. So that's when he was director of the observatory. A couple of the women I'm going to mention got bonuses of 30 cents an hour, but we're looking pretty low. Okay, so the 5 women I'm going to actually talk to you about are Wilhemina Fleming, Antonia Moria, Henrietta Leavitt, Annie Jump Cannon, and Cecilia Payne Gaposchkin, excuse me. I'm going to call her Cecilia Payne. Gaposchkin was her married name. She was one of very few women Harvard computers that actually got married and continued her work. Okay, so there were lots of other women at Harvard. I could talk about them, or I could just show you a picture of them. Hey, look! There's so many of them. This was just one snapshot, one year that they decided to take a picture of the women computers. There were actually probably closer to 50 or 60 throughout that 30-year span.
And they call themselves computers?
Yeah, so they were called computers because computers weren't a thing, and they were the ones that computed all of the math.
Yeah,
so they were the computers, yeah. They did the orbit calculations, looked at the spectra, measured very tiny things, attention to detail. Got that one right. So one of the very first women computers that Pickering hired was Wilhemina Fleming. She was born in Scotland and hired as Pickering's maid. So she was working in the observatory as Pickering's maid in the residential part where he and his wife lived. The legend goes of how she got hired is Pickering got really annoyed with one of the men that worked under him and was like, my Scottish maid could do work better, and so he brought her in and she actually did work better, and he didn't really have to pay her much, so it really worked out for him and her also. Don't get me wrong, she does really cool things. So her job was to look at these photographic plates, and each plate that they had 200 stars on it, and each of those stars had a spectra. So this is basically a celestial barcode of what these different stars are. So she looked at those and tried to analyze and come up with a classification system, because we didn't really know what stars were, what they were made of. We just knew that their light kind of looked like this. And so based on pattern recognition, she started kind of sorting them. So her classification scheme turned into one of her main contributions, which was the Henry Draper Memorial Catalog. Henry Draper was a famous astronomer back in the day, and he had an early death, unfortunately. And his wife was an heiress and wanted to continue his work, so she funneled tons of money into Harvard Observatory over a 40, 50-year span of her life and after her death. I think she contributed about $350,000 total back then, which is a lot. She bought them telescopes, gave them time, all sorts of stuff. So Wilhemina Fleming worked on this Henry Draper Memorial Catalog, which was categorizing all of these stars. She divided them into 15 types based on how much hydrogen was in them. And if you look at the spectrum, oops, sorry. It's just how many of these lines she thought had hydrogen in them. That's it. And she lettered them in alphabetical order, just randomly. A, B, C, D, blah, 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 15 down. So this was a very crass classification system, which is fine, but this eventually got replaced. And so we'll talk about this. Basically, every woman that I'm going to be speaking about had their own classification system until they found the right one. Okay, some other great things that she did was that while she was observing photographic plates, she noticed a star suddenly appeared out of nowhere. Because you can stack photographic plates on top of each other and say, oh, there's nothing here. Oh, suddenly there's something here. She actually discovered the 10th nova ever observed, which is pretty cool. So she is the owner of this nova, basically, and her name is associated with it. Sorry, for those of you who don't know, a nova is an explosion of a star. Supernova is where like it explodes and nothing's left, and a nova is like a small burp, basically. She was actually the leader of the entire computing group by 1886, and in 1899 she was given an official position as the curator of astronomical photographs. This was the first position that Harvard ever gave to a woman. And she wasn't faculty, she wasn't paid anymore, they just gave her a title, but it was still a really big deal. She also worked on variable stars. So variable stars are stars that change in brightness and color. She did some with that, but one of the other women I'm going to talk about did some really cool things with that, so we're kind of skip that and move on. Some of her biggest achievements were in 1906, she was named an honorary member of the Royal Astronomical Society in Europe. And that's a pretty big deal, to be named an honorary member as a woman. In 1911, she was named an honorary member of the Astronomical Society of Mexico, also pretty great. And her lifetime achievements include discovering 10 nova, 300 or more variable stars, so I think it was like 347 by the end of her time, 59 nebula, and she had 2 papers published in the Astrophysical Journal, which is exactly one more paper than I have.
You're young. You've got time.
I'm working on the second one now. I want to retire at least before I graduate. Okay, so Wilhemina Fleming was really like one of the first pioneers of this computing group, was kind of the like mom to everyone. And the next woman that came in that had some claim to fame was Antonia Moria. Now, Antonia Moria already kind of beat out everyone else because she was Henry Draper's niece. So Henry Draper Memorial Catalog, I wonder how she got the job. Anyway, she was actually college educated, which was a really big deal for the time, and she was college educated underneath another famous woman astronomer, Maria Mitchell. And she is most famous for discovering comets and asteroids. Anyway, so Antonia Moria took over some of Fleming's project because Fleming had a lot more director things that she had to take care of, and she came up with a new classification system because she didn't like Fleming's system. This one had 22 groups with Roman numeral names, so it wasn't the letters, it was Roman numerals, and each of those 22 groups had 3 additional divisions based on the width of the line and how sharp it was. So it's just a bunch of blurry lines, and she's like, this one is not as blurry as this one. That's important. And Pickering looked at this classification system and immediately rejected it as a waste of time. However, she went on to do some other things. In 1889, she helped Pickering confirm Mizar, which is a star in Ursa Major, is actually a binary star. So a binary star are two stars orbiting each other. And this is important for us because we can actually see Mizar if we go outside with the naked eye. If you're familiar with the Big Dipper, in the handle, I think the second one, is, if you look really closely, if you have really good eyesight, you can see two stars. The brightest one is Mizar, the dimmer one is Alcor. And Mizar is actually a spectroscopic binary, which means you can't see with your naked eye that it's two stars. But if you look at the spectra, those lines, you can tell that there's actually two stars. Because if you look at the spectra over time, you might see one set of lines. And the next time, there might be two sets of lines. And the next time, it might go back to one. So it's these stars orbiting each other. And if you look at the spectra, it actually changes, which is pretty cool. So that's really great. She found another one. And she was really fascinated with these spectroscopic binaries, but they ultimately weren't what made her famous. So we're going to skip a few years down to 1905, where another astronomer came in named hertzsprung. His first name doesn't matter, everyone knows him as hertzsprung. He used Maury's classification system of line widths and sharpness, so everything that Pickering was like, shh, that's silly, don't do that, to identify the fact that certain spectra are associated with red stars, but these red stars can be giant or dwarf. And no one had made that distinction before. So by analyzing these spectra of red spectra, he was able to break them based on the line widths and the sharpness into giant stars and dwarf stars. So that had never been done before, and Maury was like, told you so. And furthermore, in 1913, Russell came up with this idea of evolution, where the star starts as a dwarf star and grows into a giant star, and so it can start as a red star, maybe turn a little yellow before going over to red. And he used Maury's classification system for this. This turns into something called the HR diagram, which is a very famous diagram in astronomy and is still used today, where the red stars are located over here, the bluer ones are located over here, and there's some evolution that takes you from red back up to red again. Now, that's a very simplistic view of this. This was, 1913. It's been 100 years since then. We can just kind of, we'll take it as it is at face value that this was really revolutionary at the time. We know a lot more now about how stars evolve, but at the time that was pretty cool. So that was Antonia Moria's biggest contribution that hertzsprung and Russell actually get the credit for. Woo, astronomy. So Antonia Moria comes in and out throughout this picture. She and Pickering bicker a lot, and so she doesn't really come around the observatory very much. So that really is her main contribution. Henrietta Leavitt, on the other hand, is around a long time and does some pretty cool things. So what she does, unfortunately, requires a little bit more thought. And so I'm going to be saying astronomy things, and if they're a little bit over your head, please tell me, because, I was in your position like 2 weeks ago. So, Henrietta Leavitt was born in Massachusetts, and she received a college degree in 1892. So like I said, these women are getting college degrees. They're kind of a little better off than a lot of the women in the US at the time. And she was mostly deaf, which is an interesting fact. There have been a lot of women astronomers who actually were deaf. 2 of them are in my fact sheets. Yeah. She loved astronomy so much that in 1895, she became an unpaid volunteer at the observatory. So she wasn't even getting paid for what she was doing. Eventually, later on, she got paid, mostly when Pickering asked her to come back, and she said, I'm not coming back for anything less than 30 cents an hour. And so she got a pay bump. She worked on variable stars whose brightness and color change over time, as I mentioned, and she specifically looked at variable stars in something called the Magellanic Clouds. If you live in the southern hemisphere, you're very familiar with Magellanic Clouds, so these big fuzzy things that are on the sky, and they're dwarf galaxies that you can see from Earth. They're actually a part of the Milky Way galaxy. They're kind of like, how planets orbit a star, same kind of thing, they orbit the Milky Way galaxy. They're dwarf planets. And so she was looking at the Magellanic Clouds because they're doing observations both in the north and southern hemispheres. And she found all of these variable stars. And so she was studying them. And you're thinking, how do you study variable stars, stars that change in brightness? Well, what they do, which is really cool, they take these photographic plates. And so this plate in particular, the stars are black. They take a negative of a plate maybe a couple months later so that the stars are white and the background is black. So what you see when you look up at the sky. And then they put them on top of each other. And if there's a ring of white or a ring of black, that means that star has changed brightness. That's how they find variable stars. Kind of a cool thing, they just layered glass plates on top of each other. So she was really, really good at this. In fact, Charles Young, who was an astronomer at Princeton, called her a variable star fiend. The variable stars that she found were a special type called Cepheids. The reason they're called Cepheids is because someone, back then found these variable stars in the constellation of Cepheus, and so Cepheids, why not? We're really good at naming things. She took a break from that to do the North Polar Sequence, which is just reference stars for photographic plates, boring. But then published her variable star work in 1908. This catalog had 1,777 variable stars from the Magellanic Clouds. She did this all by hand. Her conclusion, which will end up being a really fundamental result that still is important today, was that it's worthy of notice that the brighter variables have longer periods. So that means these variable stars are changing in brightness in a longer timeline if they're brighter, and changing really rapidly if they're small. So the idea behind this is that the Magellanic Clouds are roughly the same distance away from Earth for all of the stars inside of them. So we can assume the distance is going to be the same, roughly, for everything that she looks at. The brighter ones, then, are not any closer than the dimmer ones, which means that those are probably their absolute magnitude. So that's probably the correct brightness in comparison. So you can figure out the distance because of this neat law called the inverse square law. So if we're standing on a football field and you put a lantern on the 50-yard line, that lantern's going to be pretty bright. It's going to have a certain size. If you were to put another lantern all the way down at the other goal, that lantern is going to be twice as far from you, and it's going to be a little bit smaller and a little bit dimmer. How much dimmer? 4 times dimmer. That's the inverse square law. It just is the distance, 1 over the distance squared. So using this idea, you can take this law, say, oh, this object that I'm looking at, this variable star, has a certain brightness. And I know, based on this relationship she found, called the period luminosity relationship, which is just here, you can say, this star is this particular brightness. It has this particular period. So we know how bright it is, and it's this much dimmer than this other star, so we can figure out its distance. That's what happened. And this is important because at this time, we didn't know that there were other galaxies besides our Milky Way. We thought everything was a nebula, and everything was one universe, and our Milky Way was the one universe. Until this great thing happened, the Cepheid relationship, because it was based on Cepheid variables, we had no way of calculating distances that far, so we couldn't figure out if things were inside of our Milky Way. So what they did was use this great relationship and calculated the distance to the Magellanic Clouds. 30,000 light years. That seems like a lot, but maybe not outside of our Milky Way. Well, Harlow Shapley, who took over Pickering's job when Pickering retired as the director of the Harvard Observatory, thought, I could use this to measure the size of our Milky Way. And so he made the very first measurement of the size of our Milky Way, of roughly 100,000 to 300,000 light years. So the Magellanic Clouds could be inside of our Milky Way, so that fit with his one universe, one galaxy scheme. And then in 1923, Edwin Hubble came around and said, wait, I observed a Cepheid in the Andromeda Nebula, because they were nebulas back then, not galaxies. And according to this Cepheid relationship, Andromeda is 1 million light years away and way outside of our galaxy. So when Shapley found out about this, Henrietta Leavitt was there, and I am so glad she was, because his exact quote upon reading this was, "Here is the letter that destroyed my universe." Because it was the one universe theory, and that's when nebula became galaxies. And that was one of the major contributions of Henrietta Leavitt. All right, on to the more famous women computers. Annie Jump Cannon. Has anyone heard of Annie Jump Cannon? Okay, you don't count. Okay, so you're gonna enjoy this. It's gonna be great trivia for you. Annie Jump Cannon is one of the leading women astronomers of this time, and still today is one of the most popular women astronomers. So she was born in Delaware, and she received a college degree from Wellesley College in 1884. She was also deaf, and she also worked there while Henrietta Leavitt was there, so they became really good friends because they had mutual circumstances that made it difficult for them to interact with other people. She joined the Harvard Observatory in 1896, and she was the first female assistant to actually use the telescope. Until then, women were not allowed to operate the telescopes in the evening because they were too fragile for it. It was going to make them sick, and then they wouldn't be able to come to work. But during her undergraduate degree, she actually learned how to use telescopes, so Pickering was like, that's fine. That's fine. So when she came to Harvard Observatory, she was tasked to do exactly what Antonia Moria did in the northern sky in the southern hemisphere. So just classifying stars. And so she begins to do this. And she goes through about 1,200 of them, and then decides that Antonia Moria's classification scheme, as well as Wilhemina Fleming's classification scheme, were terrible. And so she came up with her own classification scheme. She borrowed a lot from both of the two and created something that today is known as the Harvard classification scheme. It's still used today. It's still the standard. And it classifies these spectra based on this mnemonic device. Oh, be a fine girl, kiss me. OBAFGKM. And those are the different types of stellar spectra that classify the stars, where the O are the blue stars and the M are the red stars. Yeah.
Still being used?
Yes. Mm-hmm. Yes. Freshman undergraduates at Dartmouth learned the "Oh, be a fine girl, kiss me." Well, it's girl or guy. Yeah, it's pretty bad. That is a topic for another day.
I have a question while we're talking
Yes,
about
yes.
this. How difficult was it for all of these people to communicate with each other about stars when they all have different classifications? Was that a big issue, or was
Yes.
all stars were all classifications?
Yes, so I'm only talking about 3 classification schemes within the Harvard Observatory. There's still the entire world. Europe was doing something else. People in California were doing other things at Mount Wilson Observatory, and it was just a mess everywhere. And that's why, like, when this scheme got adopted, it was such a big deal because there were so many other ones. And it took a while, too. I'll give you some dates in a moment. Yes. She also looked at variable stars, whatever. She earned her master's degree from Wellesley in 1907, so she earned a master's degree at the time, which is pretty cool. And in 1910, her Harvard classification scheme, so this stellar spectra scheme, was adopted by the International Solar Union, so working our way up there. In 1914, she was named an honorary member of the Royal Astronomical Society, so you can see there's a pattern happening. They're becoming really well recognized, and they're publishing under their own names, which is another thing that's pretty cool. In 1918, one of her main claims to fame started happening. The first of a 9-volume Henry Draper catalog was published. So one of 9 volumes, so that's a lot of things. This volume contained 225,300 stars, all of a 9 or greater magnitude. So remember, we can only see a 6.5 magnitude, so she used telescopes to figure out the rest of them, in the North and South Hemisphere, and she classified every single one of them by eye. 225,000 stars that she classified by eye, by herself. So it was the best classification scheme because usually with classification of big catalogs like this, a lot of people have eyes on it, and so it's not consistent. This was the biggest and most consistent. And actually, an interesting fact that I just found out about, Pickering paid for this publication out of his own pocket because funds were short because of the war. In 1922, the International Astronomical Union, which is the reigning body of astronomy right now, adopted the Harvard classification system, which is why it's still used today. And then she got a lot of really cool awards, so I'm going to tell you about them because they're a big deal. Oxford awarded her an honorary degree in 1925. She was awarded the Henry Draper Medal in 1931. And in 1932, she was given the Ellen Swallow Richards Prize. This was a cash prize that she actually donated in entirety to the American Astronomical Society to establish the Annie Jump Cannon Award. This award is given every 3 years, even today, to women who are pioneers in astronomy. And in 1938, she was finally given a non-faculty position as the William Cranch Bond Astronomer at Harvard. So it took until 1938 for her to have an official position and to be recognized as an actual worker of Harvard University. Cool. Are you all with me so far? Great. The last one is Cecilia Payne, and she is amazing. I'm just going to qualify that to begin with. She was born in England. She was also college educated. She started college in 1919 as a botanist. A botanist.
Science.
It's related.
Yeah, kinda. The reason she switched to astronomy is because she attended a talk by Arthur Eddington. And in this talk by Arthur Eddington, he talked about his trip to go observe a solar eclipse, the same solar eclipse that proved Einstein's theory of general relativity correct. And in that one talk alone, she switched from botany to astronomy, signed up for all of the physics and astronomy classes she could, and gave up botany. Wow. Thankfully, that happened because she has done a lot of really great things. As she was taking physics in college, she was the only woman in Ernest Rutherford's physics class. You may be familiar with Rutherford. He did a lot with the atom and discovering all of the different electrons, protons, things like that. He used to address the class as lady and gentleman, and all the gentlemen would laugh. And it kind of put her in her place. And so from there, she became even more determined to make it in astronomy. Which, to be honest, that still happens today in a lot of physics classes. And so that's something a lot of women can really understand and relate to. So as she was going through this, she graduated. In 1923, she went out and found a ton of fellowships so that she could come to Harvard Observatory to support 1 year of research. And this was under the new director, Harlow Shapley. So Pickering at this point had retired and had died, I think, as soon as she arrived. In 1924, she passed her preliminary examination for her PhD, which is great, except that Harvard and Radcliffe College, which was the women's college associated with Harvard, didn't offer PhDs to women. And so Harlow Shapley was like, I'll talk to the physics people. And the physics people said, we're not giving a PhD to a woman. He's like, okay, we're making a new department, astronomy department. You're going to have an astronomy PhD. And so he put together the entire astronomy program just so she could get an astronomy PhD through Radcliffe College, which, since they combined, is essentially a PhD through Harvard. Anyway, so Cecilia Payne's thesis was built on Annie Jump Cannon's classification system, except since she studied under Ernest Rutherford, she had all of this knowledge about atoms and elements and how those things related to each other. She also took work from, I'm going to butcher this, Meghnad Saha, who in 1920 discovered that different temperatures were associated with different lines in spectra. So you could figure out temperature based on what the spectra looks like, which is great because she combined it all together. And as she was doing this, she worked out the chemical composition of stars. That had never been done before. We had no idea what stars were made of. She was basically the founder of standard astrophysics. Before it was just astronomy. This is astrophysics. It sounds way cooler because it's way more impressive. So her thesis, she sent to other astronomers in 1924, and it included the relative abundance of 18 different elements, and then she compared that from stars to the Earth, and was like, hey, biggest conclusion that I can think about is that stars are made of hydrogen and helium, mostly, and then there's some other metals and things like that. And she sent it to all of these other astronomers because it was this great, like, brand new thought process. And Russell, remember him? Russell. Yeah, he responded with, I am convinced that there is something seriously wrong with your theory. And so she retracted it. So it wasn't actually in her PhD. She still was able to get her PhD with the work that she had, with that exception retracted from it, and was the first PhD that Harvard or Radcliffe had ever given in astronomy, and to a woman, which is pretty great. What's funny is that 5 years later, Russell published a paper in the Astrophysical Journal that confirmed her conclusion. And upon receiving her thesis, sent a letter to Harlow Shapley saying it was the best thesis that he had ever read, maybe with the exception of Harlow Shapley's. So, some great things about Cecilia Payne. She was the first recipient of the Annie Jump Cannon Award from the AAS, the American Astronomical Society. Antonia Moria also received it in 1943, but I didn't mention it because I hadn't told you who Annie Jump Cannon was yet. Just an aside. In 1938, she was named the Harvard Phillips Astronomer, so she was given an actual position the same year that Annie Cannon was. Then she transitioned to faculty. And then she became a full professor and was the first woman full professor of Harvard. And then she became the chair of the astronomy department in 1956. She's moving her way up. And finally, in 1976, she received the Henry Russell Prize for Lifetime Distinction in Astronomy from AAS, the American Astronomical Society. So all of these great women really set the foundation for modern astronomy and astrophysics. Yeah. I do want to share a couple of my sources. This is Edward Pickering and Women Computers. You're welcome to come up and take a look. There are some pretty fun pictures in here afterwards. Excuse my post-it notes, they're everywhere. The Glass Universe, which is available on Amazon, and I think got linked at some of the Vin's posts, which is a really great read. It's not very technical. It's kind of like just a fun book literature read. It's by the same author who did Longitude and Galileo's Daughter. Here, Longitude is great. I hear Galileo's Daughter is not so great. The last thing that I want to show you is the Women in Science book, 50 Fearless Pioneers Who Changed the World. This is a young adult, young child, trying to get women interested in physics book, and it is amazing. It is absolutely amazing. Cecilia Payne is in this. This is her page, all about her. And also Katherine Johnson, which if you haven't seen the movie Hidden Figures, that's what inspired this talk. It's amazing. I've seen it 3 times. Go see it. One last thing that I would be remiss if I didn't talk about is the fact that all of the women I told you about are white women. It's a very sad subject for me. The very first black woman to receive a PhD in astronomy didn't happen until 1981. Since then, in the US, since then there have only been 17 total in the entire country. There are 6 graduate students right now who are pursuing their PhD. I know one of them, Teresa Monsu. She's really wonderful. But it's something I like to bring up because you should be nurturing everyone you can, especially women and minorities, because it's very important to get more women and minorities interested in science because they come and they provide a unique perspective. And so there are 132 women who are physicists or astronomers or some physics-related field. 17 are astronomers, and I hope that there are many, many more for many years to come. The last thing is that we may not be able to observe, but I brought some sky charts for the rest of January. There's a pile over there, and it has things that you can see with the naked eye, things that you can see with binoculars, and things that you can see with telescopes. So enjoy this. We may not be able to observe tonight, but at least you can go home and observe. The way to use this, sorry, I should explain that. Huh? Yeah. Is if you face the north, you want to point towards the north at the top, and directly overhead is the center of this. So get your compass out. There's one on your phone, I'm sure. And you can arrange yourself in that way and look from there. Now the cool stuff, which I'm sure you guys have been really anxious about, are these really cool plates that I brought, or the photographs of the plates. These are from the Palomar Observatory Photographic Atlas of the Northern Sky. And while I can't pass them around, you're welcome to come up and look at them at the end of this talk. This one, right here, in that little blobby part, is the Hercules cluster. Make sure I get these right, 391. This one, this little blobby part here, is the Crab Nebula. And they're labeled here too, so you can actually see what I'm talking about if you want to come see them. This one's pretty great because it's very easy to see. That is the Andromeda Galaxy on a photographic plate, which is pretty cool. The Triangulum Galaxy, which is right here, which is another one of our close spiral neighbors. I should note, you can see the Andromeda with the naked eye. You cannot see the Triangulum with the naked eye, but you can see it with a telescope. In fact, it's something we look at Dartmouth Public Observing, I think during the summer. Can't remember. I think fall.
Fall.
The last thing is something that's really cool. This is up right now. It's the Pleiades. If you're familiar with Greek mythology, the Pleiades are the seven sisters. And they're actually located on the back of the constellation of Taurus, because Taurus is their sworn protector, Taurus the bull. And this is what they look like on photographic plates. To the naked eye, you can see about 6 or 7 stars. It's just like a little cluster of stars right on the back of Taurus. It kind of has a shape that resembles one of the dippers, just for finding it on the sky. Anyway, thank you all for coming to my talk. If you have any questions, please ask them because I will make up things that I don't know.
Have you ever tried?
I know, it's great.
Have you ever tried Google Sky?
Yes.
Which the app, and you just hold it up to the sky and it tells you what each star
Yes.
is.
I don't have Google Sky because I have an iPhone, but there is Sky Map or something similar that is exactly like that, and I highly recommend it if you're going outside. I do recommend if you're going to use that while you're observing to turn a red filter on your phone. Blue light will make it harder for you to see things in the sky.
Right.
So I would recommend for iPhone something called Starwalk.
Starwalk, okay.
Starwalk, really excellent. Not only can you focus on the solar system, but then you can expand out into the sky.
Awesome.
And it does have a filter
Ah,
on it.
cool.
So, you know.
I'll have to add that.
And I recommend a book that I read in 1968 called Red Giants and White Dwarfs by Robert Jastrow. Is that his name?
It sounds familiar.
Yep.
I'm with you so far. Great.
So, yeah, it is probably in some way timeless, although a lot of discovery between now and then.
Yeah.
Really great, if you're interested, a great introduction, amateur introduction to the universe.
Great. Yeah.
Can I ask a question about black holes?
Yes, please.
Hawkins, I believe, has come up with a theory that black holes can evaporate.
Yes, he
How?
has. It's math.
Uh-oh.
It's all based on math facts, so it hasn't really been, I mean, we can't observe that happening. Yeah, the idea is that eventually, like, the heat from the black hole is going to give off radiation at the event horizon so much that it can, like, decrease because it's giving off mass when it gives off heat. It's very complicated.
Heat's energy.
Yeah, heat is energy.
It's on timescales much longer than the universe has existed right now.
Yes, that is also true. So they can evaporate, but, you know, in, like, 20 billion years, maybe? Astronomy works on really long time scales.
Yeah, it does.
Yeah.
You mentioned some numbers for the early calculations of the size of the Milky Way.
Yes.
What were those and how accurate were they?
The very first one was 100,000 light years, which is kind of-ish accurate. It's pretty close. It depends what you define the Milky Way at this point, because, like, you have our galaxy, but there's also something called a halo that surrounds it, and sometimes the halo is considered bigger than that. His second measurement was 300,000, and that was off. So, one thing I didn't mention is that the inverse square law is really amateur. Like, that has been cranked down into this really precise numerical, like, calculation, and 1 over d squared is just like if you're assuming things, but back then they didn't know any better. Any other questions? More about black holes?
So I read something, I don't know, this week or last week about this discovery that galaxies or some can like spit off objects.
Yes. Yes, that is a thing that can happen. The idea is that they can spit off rogue stars and rogue galaxies, not to be confused with Rogue One. And the idea is that if they have some type of gravitational interaction, somehow, like, if something's, like, not really gravitationally, like, attached to the system, that it can be easily overcome with a, velocity that just kind of, like, kicks it out. And so there could be all of these objects just kind of free-floating everywhere that we don't really know about. It's one of the ideas for what dark matter could be, are these rogue planets and like brown dwarfs that we don't know about, but
Machos.
they're called machos. Yeah, it's a good time. But that really hasn't been well established, but that is a possibility that people are looking into. That would be a lot of things to account for dark matter.
An awful
though.
lot of things.
Yeah. Yeah.
I heard of, like a couple years ago, I think, that the star Betelgeuse in the Orion constellation, that it's going either supernova or might turn into a black hole.
Yeah, so that is definitely going to happen. The definition of soon is the tricky part. Soon. So like I said, astronomy is a really long timeline. Like our sun is going to turn into a red giant soon in 4.5 billion years. It's entirely possible that Betelgeuse could do something like that. I don't think it would be a black hole though. Would it?
Yeah, Betelgeuse is it's pretty big.
Okay, it would be a black hole.
Could be neutrons.
It would definitely supernova. It's definitely big enough for that. It's going to probably core collapse because it is so big, so it'll just kind of like not be able to keep itself afloat anymore, and everything's just gonna kind of fall into the center because of gravity, and then that causes an explosion, supernova. And then what's ever left over in the middle is going to be so massive that it'll become a black hole because it won't be able to be stable.
So what is it classified now as? That way it would turn into a supernova more sooner than other stars. What is it classified?
The reason why I think it would be sooner rather than other things is because it's in a red giant state, and I think we're seeing winds.
Supergiant.
Yeah, well, it's
Yeah,
a supergiant, so it's really big. A red supergiant, and then there are winds, and winds is like the stage before all heck breaks loose. Winds spell disaster, basically. Yeah.
What does event horizon mean?
Event horizon. Oh, that's a good question. Okay, so you have this black hole thing that no one really knows what it is. We just call it a singularity so we don't have to pay attention to the math. And eventually, like, this has so much gravity that it's basically pulling everything in within a certain radius because the gravity, affects it at a certain radius, so a certain distance away. That distance away where gravity's, not even light can escape is the event horizon. So we don't really know what happens inside of the event horizon because we can't see anything past the event horizon. So if you go back to the movie Interstellar, which I mentioned a little bit earlier, the black hole that they show, the supermassive black hole, call it something like mega blah blah blah, is this kind of black blob, and then there's this light around it and kind of a light ring. Where it's black on that edge, that is the event horizon. So light can no longer escape from that point.
Hence it's black.
Yeah.
Can't get the light out.
Yeah, exactly. But other than that, an event horizon defined is just a bunch of math. A lot of black holes is like just a bunch of math, but it's basically where light can't escape it. And that can change. If a black hole is spinning, the event horizon is going to be smaller than if a black hole is stationary because yeah.
The supermassive black hole in the center of the Milky Way.
Yeah.
But there's others lurking around other places?
My research assumes that there is a supermassive black hole in the center of every galaxy. It just may not be very big.
But what about, they could be a lot smaller.
Yeah. Are the supermassive
Are there other
black-
black holes in our Milky Way?
No, well, there are no other supermassive black holes in our Milky Way.
Are there other black holes, period?
Yes, there are.
Okay.
So black holes can come about in a bunch of different ways. Supermassive black holes are obviously supermassive. They're the biggest ones. And so those are in the centers of galaxies for some reason that we still have no idea why. There are other types of black holes called intermediate mass black holes, so they're in between. And there's also things called stellar mass black holes. So these are black holes that are even smaller, but they have the same kind of mass as our star, like stars around us kind of a thing. So there can be a stellar mass black hole that's the mass of our sun. In fact, if our sun was to become a black hole, nothing would change. It would just be still in the center as a black hole.
They're stable, they're not feeding.
Yeah. No, they're stable unless they have a companion star next to them. Because if a companion star gets too close and hits its gravity area, it can start to feed. And actually, this pair of a black hole and another star orbiting it is something that a lot of people, or a couple of people at Dartmouth actually study. It's pretty cool. Yeah, so there's lots of different types of black holes.
So
Stellar ones are all over the place, and supermassive ones are in the center.
So I'm always a bit confused by the expansion of the universe.
Aren't we all?
Oh, good. I was hoping you had some insight that would help explain how everything can be moving away from everything else. Or is that no longer?
No, that's pretty correct, and it's accelerating. The easiest thing to think of is that the universe started as a balloon, and if you put 2 points on the balloon, or even like 4 points on the balloon, if you blow that balloon up, they're all moving away from each other. It's just a big balloon expansion, but we don't know if it's spherical, so that makes it fun.
Yeah.
We can assume it's spherical. We do that a lot. We assume a lot of things are spherical in astronomy. There's a joke about spherical cows. It's a good one.
So, but is the Milky Way spherical at the edges or just in the center?
So our Milky Way is a spiral galaxy. So it's fairly flat. In the center is something called a bulge. So it kind of looks like, an egg, a runny egg kind of thing. And it's on both sides. We have globular clusters that pepper the outside of this kind of sphere region. And then that's surrounded by something called a halo. So for all intents and purposes, it's a sphere. But then if you add in the dwarf galaxies, it kind of sometimes pushes that sphere out again. It all has to do with what's in the empty spaces, which is dark matter. Gravitationally, if we think about gravity, spheres are the most stable thing in the universe. And so things like to be in spherical shapes, which is why a lot of planets are in spherical shapes, because gravity. And so, yes, it's a sphere, but we can't really say that for sure unless we got to measure it, and that would be mean, knowing what dark matter looks like and what it is.
It'd be famous.
I know, right?
Yeah.
I should change my thesis to that.
Good topic for a paper.
I might be laughed at if I try that. But hey, these women probably were laughed at too. All right, any other questions?
How were they able to publish any papers at all?
Pickering was amazing.
He was.
Yeah.
Yeah.
So at first, most of the women computers didn't publish at all. Pickering published under his own name all of their results, and then in the director's note of the Harvard, it's the Annals of Harvard Astronomical, blah, blah, blah. In the director's note, he would say, Wilhemina Fleming helped do all of these things. Antonia Moria was the first one to publish, and it's because she and Pickering didn't really get along, and so she demanded that her work be published if she was to return, because she had left for a while. And Pickering was like, I'm going to give your project to someone else. And she said, no, I'm coming back, and I'm going to publish it, and it's going to be under my own name. And he said, okay. And then from there, he started to encourage the women to publish. Shapley continued this because he felt strongly about empowering women, and I think in the Glass Universe it actually talks about Henrietta Leavitt, I believe, was about to publish something, or it was Cecilia Payne, I don't remember off the top of my head, but one of them was about to publish something with only the initials of her first and middle name, and he said, are you ashamed of being a woman? Publish your full name. And so she did, and that's how she got the acclaim for that. So it was really Pickering and Shapley were just amazing and really pushed them to be their best. Which is why I had to talk about Pickering at the beginning, because he really was fundamental in all of this.
Good.
Yeah. Which is why it's important to encourage women to go after astronomy and STEM fields. Broken record. All right.
Okay.
Cool. Well, thank you guys.
Thank you.